Hi everyone, I'm Yuxin Ma, currently an assistant professor at Southern University of Science and Technology in China. Today I'm going to introduce our work on exploring the design space of Sankey diagrams for the food, energy, water nexus. This work was done when I was a postdoc in the Vader Lab, Arizona State University. In recent years, the food, energy, and water nexus has become a topic of considerable importance and has spurred research in many scientific and technical fields. This increased interest stems from the high level and broad area of impact that could occur in the long term if the interactions between these complex few sectors are incorrectly or only partially defined. For this reason, a significant amount of interdisciplinary collaboration is needed to accurately define these interactions and produce viable solutions to help sustain and secure resources within these sectors. Providing tools that effectively promote interdisciplinary collaboration would allow for the development of a better understanding of few nexus interactions, support few policy making under uncertainty, facilitate identification of critical design requirements for few realizations, and encourage proactive few realization design. The visualization approach that is often used for few visualization, or at least energy-water visualization, is the Sankey diagram. Many of the existing works choose to use Sankey diagrams in order to explore links between the food, energy, and water sectors, as well as how changes in one sector may affect another. However, as more sectors, resources, or demands are explored, the Sankey diagram representation faces significant design challenges in handling multi-sectoral relationships and exploring few nexus. To explore the design space of the Sankey diagram and optimize the design for better support of the exploration and analysis of the few nexus, we contribute a design study which proposes a list of design requirements for few nexus, a set of visualization design alternatives that attempt to improve readability and minimize the negative impact of potential visual clutters in Sankey diagrams. Also, we compare the proposed design alternatives against the traditional Sankey diagrams through a user study, where the lessons learned and future directions are also discussed. The remainder of this talk is organized as follows. First, we describe the major categories of tasks identified in using Sankey diagrams. Then, an alternative design called nest diagram is proposed, followed by an evaluation of the effectiveness of the new design. Although Sankey diagrams are widely used in many disciplines, little work has been done in the specification of task requirements to analyze the effectiveness of these diagrams. Thus, there is a problem when trying to develop new designs, since no general metric and principles can be used for evaluating the improvement of the new design compared with the original Sankey diagram design. In our work, we focus on first identifying common tasks that could apply to Sankey diagrams, and then identifying specific tasks relating to Sankey diagrams, specifically in few nexus. The summarization was conducted through a literature review and iterative discussion and refinement with domain experts from different related research disciplines, such as sustainability science and hydrology. Finally, 7 tasks were identified, including object identification, value retrieval, link analysis, path analysis, pattern recognition and column understanding, extremum identification, and intersector analysis. In the first task, we try to identify the desired nodes given a set of characteristics such as node identifiers, names, or types. When values are associated with the nodes, we need to support the value retrieval from such nodes. For link analysis, the adjacent nodes with similar or dissimilar types should be identified. The parent or the child node in the link should also be discovered correctly. Beyond individual connections, path analysis refers to high-level interactions between nodes where they are connected among multiple edges. All involved nodes and edges should be highlighted in the analysis process. Pattern recognition and column understanding refers to the identification of trends or repeated characteristics occurring within a single or multiple diagrams. The task of extremum identification refers to identifying the extreme values either locally or globally within the visualization. The values can be associated with the nodes or the edges. And the intersector analysis refers to the analysis of intersector influence and the interactions within a single or multiple diagrams. For example, to compare values in two diagrams of different years. Based on discussion with our domain experts, we identified that the task categories of value retrieval, link analysis, and the intersector analysis were identified as their major challenges in using the Sankey diagrams. Thus, we developed the nest diagram designs that incorporate characteristics from Sankey diagrams, tree maps, and graphs to improve readability for multi-sector designs, such as those found in the field systems. The majority of elements and design choices used in the nest designs stems from Sankey diagrams, including resource flows from the left to right, column-based semantic node placements, size of elements representing the amount of a resource, and the abstraction of resource flows after they pass through a node. For a nest designs, we identify 5 major design elements: nodes, sectors, supernodes, edges, and columns. Besides the main elements, small characteristic changes were also introduced in an attempt to mitigate different issues that may be experienced from the different design choices. In the sample representation of a hybrid energy-water system, we present examples for uniform-sized or scaled connection nodes according to the input-output values, as well as orthogonal or curved edges to represent the links between nodes. In order to evaluate the efficiency of the proposed design, we performed a user study that explores the speed and accuracy for each task type in our taxonomy using the proposed visualization designs compared with a traditional Sankey diagram. The dataset used in our study describes the state-level energy and water flows in the U.S. in the year, which is shown in the Sankey diagram on the right side. We use 3 different colors to represent the sectors of energy, water, and electricity. Here, we show a sample nest diagram that corresponds to the Sankey diagram in the previous slide. The color encodings are the same, and we adopt uniform-sized connection nodes and curved edges in the nest diagram. The questions for our user study were developed from our task taxonomy and our previous discussions with our domain experts. 30 questions in total. The purpose is to compare the accuracy of answers and response time of participants between the nest design and the traditional Sankey diagram. We summarize the observations of the user study in a task-specific manner. For questions in the tasks of value retrieval, link analysis, and object identification, the proposed nest design outperforms the Sankey diagrams in both accuracy and response time, while the extremum identification questions, the response time is longer for the nest design. We didn't observe significant differences in intersector analysis and pattern recognition and column understanding questions, but the main weakness of the nest designs appear in the path analysis questions, which is quite different from what we have expected. In conclusion, we summarize a set of realization design requirements relating to Sankey diagrams for the few Nexus and propose the nest diagram to handle complicated multisectoral interactions in the few Nexus. In the future, we will attempt to smooth the initial learning curve of our design, improve the performance of path analysis tasks, and further evaluate our design in visual analytics tasks. Thank you for your listening.